we're trying to understand this variety. Let's introduce a little bit of notation. So here's a variety, x squared plus y squared minus z squared. Now by that I mean the zero, so that's a polynomial. So this is a polynomial. And by v, I mean the zero set of this polynomial. This is a variety, zero set. In other words, when is that thing equal to zero? X squared plus y squared minus z squared. Now it's often useful to study level sets, not just the zero set, but level sets. You can look at, let's say, vk, which is x squared plus y squared minus z squared, let's say minus k. So that's where x squared plus y squared plus z minus z squared is equal to k, right? That would be the level set of that. And we can try to understand all of these together. And notice I didn't specify what x, y, and z are. So for example, if I want the real points of v, so v of r, this is the real points. Whereas v of z, that's the integer points. And v of q would be the rational points. So I can specify what the universe is. Are we talking about real points, rational points?
So for v of k, so it's like, so the solution to that polynomial is equal to k?
When it's equal to zero.
Okay.
So when exactly. So so it's the same thing as saying x squared plus y squared minus z squared is equal to k, as opposed to equal to zero. So I added a shift.
Okay.
Now this is no longer homogeneous, of course. You can homogenize it, but by adding an auxiliary variable. We'll talk about all that kind of stuff later. It's often useful if you're going to find, the real points of integers are of course subsets of the real numbers. Although this is kind of a funny thing. If you so you think of the real numbers as a number line, right? You haven't had necessarily real analysis, and you haven't constructed formally what the real numbers are as, for example, Cauchy sequences of rational or something like this. So what I'm writing here is a slight lie, but it's good enough. It's true. It's just it has to be made sense of if you want to do this formally. But if you think of the real numbers as the real number line and the integers are certain this lattice sitting inside the real number line, then certainly we can think of the real points as sitting inside the integer points. If the set of real points is empty, then there's nothing to do. There are no integer points because there's no real points. So for example, if I have a variety, let's call it W. W is the variety x squared plus y squared plus z squared plus 1. What are the real points of that? Okay, so other than Sheik, Alex?
Try to make it equal to 0.
Yes, by this I mean what are the real solutions to this equals 0? And so, Alex, why none?
Just for any variable x, y, z, it'll never be negative because
Yep, you're summing 3 squares and then adding 1. This is going to be positive, this is going to be bigger than 1, you're never going to hit 0. So this is the empty set. And so we don't have to worry about, if we're trying to understand the rational points or the integer points, we don't have to worry very, very much because there aren't any real points. So there are not going to be any rational points, so there are not going to be any integer points. Sheik.
So the level curve, so the level varieties can also be you can replace k with a complex number also.
Yes, we could replace k with a complex number. We could also think of w over the complex numbers. And that all of a sudden is non-empty. Now this is a, what is this? It's a complex surface. It's a 4-dimensional complex surface, 4 real dimensional, 2 complex dimensional surface. Okay, we're not here to do algebraic geometry just yet, or at least not in any serious way, but let's just point out that this is not empty. Okay, back to, that was just an aside. Back to what is V of R? V of R, so this is a real surface in R3 What makes it a surface?
Well, if you go back, like, I guess, to Calc 3, when you have like a surface and you have to define level curves.
Yeah?
No, that's kind of like a surface.
Okay, good. We're going to come back to exactly that question in a second. Stephanie, thank you.
Wait, why is it a surface, you said?
Yes.
I was thinking the same thing as him.
Well, how can you count on your fingers to figure out it's a surface? How many variables do we have?
With three, oh, it's 3D.
It's 3 variables and 1 restriction.
Right.
If we had 2 polynomials, if the variety was given by x squared plus y squared minus z squared and x plus 1. So if I add an extra polynomial, that would be now 2 restrictions, and that would be like taking a level set, like slicing through that cone. And oh, I gave away what it is. Right. The question is, so what is this real surface? In other words, I'm making a very simple question sound very complicated. What are the real solutions to x squared plus y squared equals z squared? What does that look like?
It's just a ball?
So if it was x squared plus y squared plus z squared equals a number, it would be a ball. So in other words, if I put here minus 10 instead of plus 1, that's the radius square root of 10 sphere. But because I have not 3 pluses, but plus plus minus, so what does this look like? So what is the set of x, y, z with x squared plus y squared equals z squared? Yeah, kind of like that.
Because like if you, let's say if you pick Z,
Yes?
then you get like a circle, but then you change Z again, you get another circle. Another
Yes.
circle. So it's like this.
Okay, so Sheik is saying that when we fix z, we will get something, so it's radial in x and y. We can use cylindrical coordinates to understand this, right? But so this is radial in the xy plane. So use cylindrical coordinates. You guys have had multivariable calculus. Okay, so what are cylindrical coordinates? Other than Sheik? Oh, I'm sorry, I'm pointing in that direction. Don't tell me. I'm sorry. Don't tell me. I have to see it. If I see it written, Dibendro.
Yeah.
Dibendro. Sorry, Dibendro. Thanks for correcting. Dibendro. Other than Dibendro. Or you were about to tell me something. Or you already told me something.
Yeah.
You already told me what the solution was. What are cylindrical coordinates? You guys remember? What's x, y, z in cylindrical coordinates?
It's like the radius to the point and the angle from.
Yeah. So you think of cylinders. So the z direction is still the z direction, and then you have a radius and an angle. This is hard to see. Maybe I'll do it here. There's an angle. That's still not very good, but you know what I mean. Cylindrical coordinates. So x, y, z turns into something z. Z remains unchanged. What does x turn into? R. Right. So you're right. The new parametrization will be r theta z. The original x is replaced by r sine or cos. It doesn't matter. I mean, traditionally you would say cos r sine theta and z. Okay, so that's cylindrical coordinates. So Dibendro is suggesting that we use cylindrical coordinates to understand that parametrization, to understand that variety, the real points of this variety. And how do we use cylindrical coordinates? So let's plug this into our equation that we're trying to study, that we're trying to understand. So we have r cos theta. We want x squared plus y squared equals z squared. So what is x squared plus y squared? R squared cos squared plus r squared sine squared is r squared. So this is in V. This is in V of r, implies r squared cos squared plus r squared sine squared, better known as r squared, is equal to z squared. So what does that look like? Daniel, right?
That would be 2 lines.
Yep. R equals plus or minus z. So in the RZ plane, we have the line r equals z and r equals minus z. And all you do is you take that and you spin it in the theta direction, because it's theta invariant. So what happens when you spin this in the theta direction?
You get a, you get a surface.
Yes, what's the surface?
It's not hyperbola. I forgot the name of it.
Other than the Bendro. Yeah, cone, right? You take 2 lines, you spin them around. It's an ice cream cone. Okay, so V of R is, you take these, so here's R3, you take these lines and then you spin them. So it's this infinite 2-sided cone in all directions. Okay? Does that make sense? For whom is this too fast? Karen, right? Will you raise your hand? For whom is this too fast? No, you're just taking off your hat, chic. Fake out with the hat on. Right. Okay. So you guys are following? Everybody's with me? Okay. So what about V of z? Where's V of z here? Where are the integer points of this in this cone? Real cone, real surface.
Just that 1,
Stephanie.
1, 2, 2, 3, 3.
What do you mean 1, 1? So I have
The point.
triplets.
Oh, okay. 1, 1, 1, 2, 2, 2.
Well, 1 squared plus 1 squared is. So for example, here's 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5.
Okay.
That is 3, 4, 5. And here is a bunch of other points. And here's 3, 4, negative 5. 3, 4, negative 5.
Okay.
Okay, so it's these freckles. So the Pythagorean triples, that V of z, are the freckles on this cone, V of r. Okay, and we're trying to understand their parametrizations. Now, some of them, does that make sense? Don't tell me, William?
Yeah. Can you just say that again?
Yes. The integer points of the variety
Yeah.
are discrete. They're the intersection of this variety with z3.
Okay.
Because we want only integer entries for x, y, z. And what does that look like? It might be empty. It might be a whole lot of things. In this case, in the case of Pythagorean triples, there's infinitely many Pythagorean triples. And so that's these dots, these freckles, on this smooth, it's smooth except for this cone point at the origin, variety, whose geometry is a cone. Karen.
It's not the entire plane because they're not all real solution, or not all real solution.
What's not the entire plane? V of z?
Not the entire surface of the plane.
It's not the entire surface because the surface is continuous. So it takes all real values on the cone, whereas we only want the integer values, if that's what we're interested in, and we are. And so that will be these marks around the cone, these discrete points. Okay? So do you have kind of the geometry in your head about what it is that we're parametrizing, what we're understanding? We're understanding these points. There's yet another point of view on this. Oh gosh, I wasn't going to go into it, but it's kind of cool and important to see. What about V of Q? What about rational solutions to the Pythagorean equation? We discussed this, maybe not last lecture, the lecture before. There's a strong relationship between these two. Does anybody remember what it is? Stephanie?
If they're rational numbers, there must be integer roots.
Yes. because it's homogeneous, because the polynomial, because we're not taking level sets, we're just taking the homogeneous polynomial, x squared plus y squared minus z squared equals 0. Whenever you have a rational solution, you can multiply through by all of the denominators and get an integer solution. So the rational solutions, I can multiply this by a tenth, and that gives me 3/10, 4/10, 5/10 down here somewhere. But I could also multiply it by 1 over 100, and so the rational solutions, let me draw a new cone here. Here's the same cone, v of r. The rational solutions are dense in the real solutions. Because the real solutions, the rationals are dense in the reals, and I mean this isn't something that happens all the time. Sometimes you have lots and lots of real solutions and 0 rational solutions, and hence 0 integer solutions. Okay? This is the kind of thing that we want to start thinking about. In fact, the whole course will be a basic generalization of this picture, trying to understand what can we say about rational solutions, what can we say about integer solutions, and we will need to understand all of the completed solutions, the real solutions and p-adic numbers, which we'll get to soon. So there are these rational solutions everywhere, but actually they're not new. They're not new from the point of view of projectivizing these integer solutions. So let's see if we can make sense of that. So for any let's just recall let's make this a lemma, maybe. Lemma. For every rational solution, for every vector in this variety on the rationals, there exists, let's make it unique, a unique, let's call it W, in the integer solutions, which is primitive. So this means primitive. And there's one other thing I have to say, but let's say this like this, with W equivalent to V. We're going to define all of these things. So again, for those who are just coming in, I'm going a little bit faster just to see how we do at a faster pace, and we'll pull back from a faster pace to, I think last time we were going a little slow. We're going to go a little bit faster, and but still, by all means, if you don't understand something I'm saying, stop me and let's talk about it. So this lemma isn't quite right as stated, and I haven't defined this. So let's define this, where if I have two vectors, let's call them u and v, I'll say that they're equivalent if what's the thing we just talked about, how this polynomial is homogeneous, and so we can do something to any solution to get another solution. Yeah?
You can scale it.
You can scale. You can scale. Tell me your name again.
Charles.
Charles. Great. Yes, so as Charles said, you can scale. So if u is just a scalar multiple of v, yeah, scalar. Well, do I want to say real scalars or rational scalars? Let's just say real scalars. I think that will help us see a little bit how this is going to go. Okay, so what I mean is, you can, whenever you have a rational solution, you can rescale it and get an integer solution, which is not only just some integer solution, but a primitive integer solution. Charles.
Wouldn't the lambda have to be rational?
So in the setting, so there's a general equivalence relation that we're defining on the cone. Two things are equivalent if one is a scalar multiple of another. By the way, non-zero. We don't want, 0 shouldn't be equivalent to anything. 0 is a special point. So you're right that if you have a rational solution, which is a scalar multiple of an integer solution, that scalar is a rational. So this equivalence can be just over the rationals. But let's think about it in general over the reals. There's one more thing missing to make this unique. I claim it's almost unique, as stated, but it's actually not unique because there's one more thing that you could do. So 3, 4, 5 is a primitive point. It should be the unique primitive point equivalent to itself. It's also a rational point. I'm claiming it's unique, but actually there's something else that 3, 4, 5 is equivalent to. Charles? -3, -4, -5.
Yeah.
So -3, -4, -5 is also equivalent to 3, 4, 5. If we want to make this unique, we have to take not just the primitive points, but the ones in the positive cone. So this is the positive cone. This is z greater than 0, part of the cone. And now this lemma is exactly what we proved last time. The proof is, if you have a rational, then it's x is p over q, and y is r over s, and z is t over w in lowest terms. You multiply through by the 3 denominators, you get an integer solution, and that integer solution is because everything was reduced, is primitive, and if z isn't positive, multiply it by -1 and make z positive. And that uniquely determines this integer point. Does that make sense? So what is, well, okay. I guess I should give you an exercise. Exercise. I think writing out a proof of this lemma is a good exercise, actually. Exercise. So this is for next Friday. Exercise. Even though we already discussed it and I gave you the proof, it's a good exercise to write it out formally. So this is now exercise 1 for the week. Write out a proof. Complete proof of this lemma. Yes?
We can assume
Depends,
it's
right?
we can assume it's an equivalence relation.
Good question. Should I ask you to also prove that it's an equivalence relation? Yeah, I think that's a good sub exercise. Maybe exercise 0. Exercise 0. Verify that this is an equivalence relation.
Was that supposed to help with proving the lemma? Was
No.
that another thing?
You can assume, in exercise 1, you can assume that this is an equivalence relation. All this is, all I'm saying is, after changing by a scalar, there should be a unique integer point, which is primitive and in the upper cone, instead of the lower cone. Exercise 0 is a separate exercise, which is a warm-up for exercise 1, although it's completely independent. Verify that this does indeed define an equivalence relation. Now, what is the cone up to this relation? Before we look at the integer points, or the rational points up to this relation, what is the cone up to this relation? So let me see if you can see both of those. Let's turn that off, please. So here's a question. What is V of R modulo equivalence? Or maybe just the positive cone up to the equivalence. Maybe answer both questions. Take 2 minutes. Think about it. See if you can figure out what the hell is going on. Talk to your neighbor. So I'm saying if I take all of the points on the cone, either the full cone or just the upper part of the cone, and I mod out by this equivalence. In other words, I identify any 2 points that are some scalar multiple. That's why I want real scalar multiples. Any 2 points that are real scalar multiples of one another should be identified. In other words, pi squared and whatever is the square root of pi squared plus pi to the 4 is some random point on the cone. That should be equivalent to any multiple of it, of any real number. What is that geometrically? So think about it. Give me a thumbs up when you think you have an answer. And if you don't have an answer, then argue with the person next to you about what you think your answer might be. Take some complete random stabs in the dark. See if you can make sense of this.
The relation is, I think, different by a scalar, right?
Yes, it's right up there. 2 things are equal if one is a scalar multiple of the other. So think about these vectors in space. 2 vectors are equivalent if they're basically in the same direction. So what if you take this cone and you say everything is equivalent if it's going in the same direction? What do you get? So you guys think you have an idea? Okay. Talk to your neighbors, see if they agree. Daniel, you think you got an idea? Stephanie, you have some idea?
Not really.
So draw a picture. Draw a picture of a cone.
Mod out by that equivalence class.
Yeah, can you give me something, can you give me some fundamental region, some like representative for everybody in the class? So the question is, can you give me for every element in the cone, can you give me a representative? So someone equivalent to it. So when we looked at these rational points, well, I'll make that point in a second. Let me let people argue for a minute. Let me pause you for 1 second and say again why I'm asking this question. We looked at the rational points, and we found that if you want to study the rational points, actually you don't have to study the rational points. It's enough to just study the integer points. In fact, just the primitive integer points. In fact, just the ones in the upper cone. Because every rational point is uniquely one of those and then some scaling. And so the question is, if we weren't looking at rational points, if we were looking at real points of the variety, let's say the upper cone or the full cone, what is the full set of representatives up to this equivalence of that cone? So can you give is there some nice set of representatives you can give that will exactly, so the rational points are exactly parametrized by the primitive positive integer points. What are the real points parametrized by up to this equivalence? That's the geometric question. I want to stretch your mind to try to see the answer to it. So again, so you think you guys got it? Okay, so talk amongst yourselves. No? Yeah. Well,
That's just like an equivalence. It doesn't matter what's over. The set of all things that are equivalent to that. That's the kind of this is much on that. Yeah.
you guys are really, really close. Really, really close.
That was our success. Last lesson. That was like one of the harder things to graph.
There's one very, very annoying slight technicality that's the difference between the two.
I mean, I liked it, but it was yeah, it was challenging. Yeah. Yeah. Yeah, that was definitely a lot. I honestly chose it because I thought
some ideas or totally don't even know where to start?
I felt like it was good. And it was just,
How about you guys?
Seems to be tough. Which is my fault.
Okay, so
Yeah.
let's talk about it. Let's talk about it, because some of you got it, some of you have some ideas, and some of you are totally stumped. So there's no embarrassment to being totally stumped. Can you please raise your hand if you're totally stumped? Okay. Can you raise your hand if you had some idea, but you're kind of not sure that you got it all the way? A couple, and think you totally got it. I know you guys. You can raise your hand. I think you got it. We discussed it. Okay. All right. So, how could you try to figure this out? Well, I would just draw the cone again. Let's look at the cone one more time. So let's first work this out. So I just want the upper cone. Here's the upper cone, VR plus. Now, if I have some point on here, how can I make it as simple as possible, right? These rational points, they can be very complicated, but actually they're not that complicated. Once you multiply by the denominators and exactly the denominators, you get this primitive integer point, and that's as simple as it can be. How can I make this point, whatever it is, as simple as it can be? Well, any point, there's kind of no distinguished way of making that point simple. It's going to be equivalent to everybody else on the line. So there's a whole line through the origin. This is what everybody is equivalent to. In fact, it goes all the way down to the negative cone, but we're just dealing with the upper cone right now. So is there any way to distinguish one of these from another? Is there like some good way of saying, all right, let's just call this the guy that represents that entire line? Kevin?
Maybe like a gradient around whatever the circle is.
Yes. At what height?
Like, I guess at anything.
At anything. For example,
Pi over 3.
pi over 3. Yeah, sure, why not? Pi over 3. Pi over 3 is as good a height as any. So here's pi over 3. Let's see, pi is 3.14, so it's like 1.0 whatever. It's a little bigger than 1. How about just 1, by the way? So here's z equals 1. So your height will be just slightly higher than my height. But here's z equals 1. What happens when you intersect this variety with the plane z equals 1? So z equals 1, any x and y, but we're at height 1. So that's the plane. It's going to go straight across. Here's height 1. And what happens to the intersection of that plane with the cone? It's a circle. It's a circle. And that circle will hit one and only one line from the origin for every direction on the cone. So what have we done? So we take a point x, y, z, which is just a real point, and all we know is that z is bigger than 0. We can make it simpler by rescaling by, we want to make it land on the cone z equals 1. So let's scale it by, so I'm allowed to multiply by any non-zero real number. Tell me your name. Surya.
So could you multiply by 1 over z?
Yes. Yes. Let's multiply by 1 over z. We get x over z, y over z, 1. And that's a real point on the variety. And that is as simple as you can get, because you have complete freedom for the rest of the circle. Does everybody see that? So the upper cone, modulo the equivalence, here's a nice set of representatives for that equivalence class. The one where z is equal to 1. What is that geometrically? It's just the circle at height 1, which is the intersection. Depending.
For the unit circle, if you find all like the integer solutions on the unit circle, would that just be the modular representative for your c?
Save your question for like 3 minutes, because that's exactly where I'm going. Almost. I'm almost ready for it. Let's finish this exercise, and then let's answer your question. So, does everybody understand this? Does everybody follow this? Any questions on this? What I mean by, we solved the first problem. First problem was, given any point on the upper cone with z positive, what can I rescale it by? I can rescale it by 1 over z, and that'll make z equal to 1. And so that's a complete set of representatives. And so geometrically, what is this cone modulo this equivalence? It's just a circle. Okay? Take 2 minutes. Let's see if you can answer this question now that we've answered the first one. Talk to your neighbor. Argue, discuss. Is it the same thing? Is there any difference? Daniel, you got something? Same thing? Something different?
Something different.
Something different, okay. You guys don't have to whisper. Now's the time to talk, to argue. What do you guys think? Well, did you draw a picture? That's what I'd recommend. Can you or can you not just do the same thing? Sri, you think you got it? Would it or wouldn't it? Okay. Okay. Yeah. 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 Anybody think they got an answer? Raise your hand. Okay. Anybody still working? You guys are still working? I'll give you one more minute. Let me pick on William. Are you guys still chatting? Still working on it? You think you got it?
I don't know about that.
Okay, just tell me what you're thinking. It doesn't have to be right.
I was thinking it was like the same thing, because couldn't you just like scale the first one by the minus 1 over z?
Yep.
And then it's the same thing.
Yeah. So if we look at the whole variety, whether this is positive or negative, we can still scale it. So if it's negative, you still scale it by 1 over z. 1 over z is negative. So you can still scale this too. So scale by 1 over z, and you get x over z, y over z, 1. So that's this unit z equals 1 circle that parametrizes all the points. Daniel?
Wouldn't you also need a point at the origin?
Yes. There's one thing wrong with this, which is that you can't see that. That's a 1 over z. 1 over z if 1 over z is not 0. The reason I don't want things equivalent to 0 is a fundamentally different point on this variety. The upper cone doesn't include 0. The upper cone, maybe you didn't notice, but I was actually careful to not include 0 in the upper cone. A lot of things are much nicer in the upper cone than in the variety itself because you have this point 0 in the variety. So the upper cone, where it's not singular, excludes the point 0, and we do not want to say that things are equivalent if they're multiplied by 0, because then everything shrinks down to 0. Everything's just multiply any point by 0, and everybody's equivalent to 0, and there's no geometry left. Okay? So the only thing that goes wrong when we look at the full variety is this is unless z equals 0, in which case you're scaling by infinity. You can't get the point from 0 up to the height 1 circle. So this variety up to equivalence is equal to this same circle. That's a circle at height 1, union, disjoint union, the origin. Okay, so there's one extra point on this variety which is not on that variety. That makes it disconnect. Does that make sense? Is everybody with me? Should I give you, let me give you an exercise. This is a real exercise. Exercise 2. What is a 3D picture of V1 and V negative 1. So these were the varieties. Vk was the k level sets. So V1 is x squared plus y squared minus z squared minus 1 equals 0. What are the real points of that? V minus 1 is x squared plus y squared minus z squared minus negative 1 equals 0. Work out what these varieties look like. Homework. Let me not give you a hint. Let me actually give you something to do. Okay, so this is exercise 2. Is it going to be a cone? Is it going to be a sphere? What's the shape? It's going to be some kind of shape. I want you to think about it. And okay, you can just go home and open Wolfram Alpha and say plot this thing, and it'll show you what the picture is. And you'll go, okay, that's the picture, and you'll do some hand-drawn version of it. Don't do that. Try to really figure it out on your own from first principles. Actually, from very simple, there's no reason not to do exactly this. They're still going to have this symmetry, so you can reduce it to a curve that you can draw in the plane. Draw that curve on your own. It will really make it stick in your mind much more than if you just tell the computer, give me all the points. Oh, there it is. I get it. You write down the answer. Okay? All right. Now, back to Debendra's question. What about, so if the real points up to equivalence, at least on the upper cone, are a circle, can't we think of the rational points? Isn't there another way of thinking about the rational points up to equivalence? We could do the same thing with the rational points, right? So another set of representatives, another set of representatives of V, let's say in the upper cone of Q, up to equivalence, is this circle, the rational points on the circle, by the same process. If I have x, y, z in here, in the rational points, in other words, I have a rational number x, rational number y, rational number z, with x squared plus y squared equals z squared, I can turn that into is the set of x over z, y over z, 1 on this unit sphere. at height 1 in the plane, in space. So in fact, what have we done? We've parametrized So, what's x over z if x and z are both rational? Rational. These are rational, and this is rational. Y over z and x over z are both rational. We've parametrized the circle. We've given the rational points on a circle. That's what the Pythagorean triples are. That's why Pythagorean triples are so fundamental, because the circle is fundamental and rationals are fundamental. Let's just write that down. That is why Pythagorean triples, by which I mean the integer ones, are fundamental. They parametrize rational points on the circle. Of course they do. Think about the circle. What's the equation of the circle? Unit circle. Yeah, x squared plus y squared equals 1. Okay, if x squared plus y squared equals 1, and what are the rational points? So this is the circle. I guess if I want to write this as a variety, I'll say minus 1. Well, let me leave it as is. So this is the circle. The one sphere. This is just notation for the one sphere. Circle, fancy way of saying circle. That's the circle. What are the rational points? So here's a nice exercise. What number is this? 3? So x and y are on the circle, and rational implies they have the same denominator. And primitive, of course. So this is r over s, and this is t over u, with r, s, t, u integers, and reduced implies s equals u. Do you understand the exercise? Prove that if you have a rational point on the circle, if x and y satisfy x squared plus y squared equals 1, and x is r over s in lowest terms, and y is t over u in lowest terms, then s equals u. The denominators have to be equal. And if the denominators are equal, does everyone understand the exercise? Do you think you have some idea of how to prove it? Okay, you'll think about it. You'll think about it. See if you can make sense of this. Again, office hours, 1 o'clock today. This isn't due until the following Friday, so you still have this weekend, next week to think about it. But given that this is the case, so given this exercise, so if I have a point r over, let's say, u, comma t over u, in lowest terms, on the unit circle, as a rational point, that happens if and only if, what do you know about the vector r, t, u? It's an integer Pythagorean triple. Let's say u is positive. We may as well, right, we have a choice of multiplying all, we can scale t, u, and r by a minus sign, and that doesn't change the point x and y, because minus over minus and minus over minus. So we may as well assume that u is positive. And primitive. Because if they weren't primitive, they'd have some factor in common, and then these fractions wouldn't be reduced. That's what makes the Pythagorean, that's why Pythagorean triples appear everywhere. You don't think about it. You're thinking about the cone. Cone is something complicated. No, it's not. It's just a circle. It's a fancy way of writing a circle and stretching that circle out so you can see the denominators. That's what Pythagorean triples are. They're rational points on the circle, stretched out so you can see the height, the complexity of this rational point. We're going to get to what notions of complexity are, but one notion you could say, a rational number gets more and more complex if it needs larger and larger denominators in order to be written. This is showing you that exactly by saying its height is literally its height by putting it on a cone. Cool? You guys see that? All right. So that's why kind of Pythagorean, every single civilization, as I said, the Babylonians were playing with this, the Egyptians, the ancient Greeks, obviously, Indians, Chinese, every civilization that bothered to ask any question remotely related to rational points, integer points, stumbled onto this equation. X squared plus y squared equals z squared. Because they all stumbled onto the circle, one way or another. All right. So what did we do? So let's recall what we finished last time. So we proved the parametrization of these primitive, let's say, integer points, and there's one extra symmetry, which is there's a symmetry across the line that reflects between x and y. And we saw that if you have a primitive solution, one of x or y has to be even. That's the only way to do it. Intersect where y is even. We just arbitrarily chose y to be the even one. So if we have x, y, z in here, the parametrization was, so if it's primitive, z is positive, y is even, then what do we prove? There exists anybody remember? We had some way of saying exactly what x was and exactly what y was and exactly what z was in terms of two auxiliary variables. Devendra.
So z was r.
Yeah. So there exist integers r and s, in fact co-prime, with z equal to r squared plus s squared, x equal to r squared minus s squared, and we made y the even one, 2 r's. And everybody remembers the proof. In fact, this parametrization, at least naively at first, is just a real parametrization. If you don't care about r and s being integers and being primitive, this actually is yet another way of seeing the same thing. It's a real parametrization because what's the formula for r and s? I mean, this is kind of a reproof or a summary of the proof sketch. What's r? You can write it down as an expression in terms of x, y, and z. Actually, this is a good exercise. We didn't do this explicitly last time. Let's take 5 minutes and see if you can look back over the proof of this parametrization and figure out what r and s are explicitly in terms of the other variables. Want to do it? Yeah, take a minute. Remember the proof? Okay. I'll give you a hint. We started with y squared equals z squared minus x squared. That was the beginning of the argument for how to find r and s. And cheat. Now's the time to cheat. Talk to your neighbors. Look over their shoulder. No, y squared. So x squared plus y squared is z squared. So move the x squared to the other side.
Oh.
That was the first step in that parameterization.
Yeah, okay. You could also do it like this. Other than z turns that's
And you can simplify this. Make it look like that. Yeah, okay. Dipendra is pointing out that you could just cheat and solve exactly from here. I've given you R and S in a way that you can solve for what R and S have to be in terms of the other variables. Say it again?
Is that R in terms of X, Y, Z, right?
R and S in terms of X, Y, Z, yes, exactly. I mean, X, Y, and Z have a relation between them, so you only actually need two of the variables. Two variables determine the third. Everybody's still working, okay, good.
This is so Y squared, Z squared minus Y squared is Z squared.
Is anybody totally stuck and doesn't even know where to start? Okay. Everybody's working away. Who's solved it already? Okay. Karen, you got it already? Great. You can basically eyeball it here. If you add x, I mean, this was basically the proof, right? The proof was to start with y squared equals z squared minus x squared. Z squared minus x squared factors as z plus x and z minus x. Both of those have to be even because z and x are both odd. So if you divide that by 2, that's going to be some number, and then we argued that number has to be a square. I'm just reminding you of the argument. But if you just look at the formula, so what is z plus x? 2r squared. In other words, so z plus x, z plus x is 2r squared. So z plus x over 2 is r squared. So z plus x over 2 square rooted is r. And z minus x is z minus x. I have r squared plus s squared minus r squared minus s squared, 2s squared. So z minus x is 2s squared, so over 2 is just s squared, and the square root of that is s. And then if you multiply 2rs, that's 2 times square root of z squared, z plus x times z minus x. Z plus x times z minus x is z squared minus x squared. But the equation says x squared plus y squared equals z squared. So z squared minus x squared is y squared. The square root of that is y. And there's a 2, square root of 2 on both of these that is canceled by that 2. Okay? So if I said that too fast, just do the algebra again at home. But my point is, this is a completely real parametrization. Anytime you have real points, x, y, z, you can make real points. Z will necessarily be bigger than x. In the upper cone, yes. In the lower cone, you have to be careful because z could be negative and x could be positive, and then this is definitely negative. So let's stick to the upper cone. In the upper cone, z is an upper bound for x. So these are always real numbers, and that's a parametrization. What's fascinating is on the integer points, on the primitive integer points, r and s have to themselves be integers. That's what we proved last time. Do you remember how we proved that? In the interest of time, let me remind you, you can look back at your notes. The reason, okay, so this is, just remark, this holds for v of r, at least in the positive cone. Just as well, what's amazing is that, well, until you see the proof, what's amazing is that r and s are integers if the original point was a primitive integer point. Okay, how did we prove that? Let's recall y. So y, the reason's very simple. Y squared equals z squared minus x squared. That we factored as z plus x times z minus x. This we wrote as twice some number a. This is twice some number b. Y is even, so this is 4 times some number y1 squared. You guys giving me thumbs up? Yeah, slide it up. And so we have this equation, y1 squared is a times b. But x and y, x and z are co-prime, so a and b are co-prime. And two co-prime numbers multiplied to a square, that can only happen if each of them is itself a square. So a is actually r squared. So these are co-prime. This is where we use, crucially, the coprimality. Co-prime, and a times b is equal to a square, the square of an integer. That means a is some square and b is some square. And these squares are co-prime to one another. These numbers r and s are co-prime to one another. And if you just write back out what a was z plus x over 2, so r is the square root of that, and b was z minus x over 2, and s is the square root of that. Okay? Is this all ringing bells? Coming full circle? Good. So we have this parametrization. I think, even in the short time left, we can prove Fermat's last theorem. This parametrization and a little bit of messing around and playing are enough to prove Fermat's last theorem for the exponent 4, which is how we started here. So let's do it. Any questions so far? Everything I'm saying makes sense? Let's prove Fermat's last theorem. Let's see. I want to see the parametrization. How do I do this? I want to keep the parametrization. This is the thing that I want. So, Fermat's last theorem for n equals 4. It says that x to the 4 plus y to the 4 equals z to the 4 in the integers has only trivial solutions. There are no non-trivial integer solutions to this. In fact, we're going to prove an even stronger theorem, what Fermat really proved. And this, I think I mentioned last time, there's no way, no one believes that Fermat really had a proof for all exponents, even though he claimed it. This one, he really did have a proof, and he explained what the proof is, and it's a brilliant idea. So, what Fermat really proved, so this is the theorem. It's an even stronger theorem. You can't even solve this equation over integers. non-trivial. So if you can't even solve this equation, suppose you have a solution to x to the 4 plus y to the 4 equals z to the 4. Well, z to the 4, you can say x, y, z squared solves this equation. So the reason this implies, so let's call this theorem A. So theorem A implies Fermat's last theorem because, well, let's look at the contrapositive. If there is a solution to Fermat's last theorem, if x, y, z solves non-trivially x to the 4 plus y to the 4 equals z to the 4, then the vector x, y, z squared solves x to the 4 plus y to the 4 equals z squared squared. And that would be a solution, an integer solution to this equation. But this equation has no integer solutions, so this equation has no integer solutions. Does that make sense? Okay? So theorem A is what we're going to really prove. Now let's look at theorem A. I want to look at theorem A together with the parametrization. Here's our parametrization. Here's theorem A. Let's try to look at these two together and see where there is an inconsistency. So suppose we solve this equation. X to the 4 plus y to the 4 equals z squared. If x to the 4 plus y to the 4 minus z squared is equal to 0, then x squared y squared z is a Pythagorean triple. We can assume this z is positive. These are all integers, so their squares are integers. Now, can we assume coprimality? So if x and y have a factor in common, then that factor to the 4th is in common. That factor to the 4th pulls out, and this z squared has to be divisible by it, so z has to be divisible by the square of that factor. In particular, they will no longer have a factor in common. Okay? So if there's any factor in common between two of them, a similar argument will say, maybe I'll leave that as an exercise. Here's an exercise. What number are we? 4? Exercise 4. If x to the 4 plus y to the 4 equals z to the g squared, and any two have a common factor, then all three do. So this is again saying primitivity implies pairwise primitivity. If all three have no common factor, the only thing that divides both x and y and z is 1, then any two of them do. Okay? Good. So there's a couple of cases here to consider. If x and z have a factor in common, if x and y have a factor in common, if y and z have a factor in common, that's actually equivalent to x and z because there's a symmetry across x and y. I'll let you think about that exercise. Okay, so this exercise is show this primitivity. So let's assume we have a primitive. So we can assume we have a primitive that they don't have a factor in common. Because if they do, then I can scale x and y by that factor and z by the square of that factor. Z will if x and y have a factor in common, z actually has the square of that factor in common. So we can assume that it's a primitive solution. And now we can apply our theorem, our parametrization. So what's the Pythagorean triple? It's not x, y, z, it's x squared, y squared, z is a Pythagorean triple. And the parametrization says there must exist, anytime you have a Pythagorean triple, there must exist numbers r and s So by parametrization, there exist integers Rs so that x, y, z, except it's x squared, y squared, z, such that x squared, y squared, z has that parametrization. And you remember what it was? Z is r squared plus s squared, y is 2rs, and x squared is r squared minus s squared. And something very bizarre has happened. Something very bizarre has happened. We started with this Pythagorean triple, x squared, y squared, z, and we got a Pythagorean triple s squared, x squared adds to r. This is going to be the thing that kills the equation. We're not going to get we're not going to get the full solution today. There's a couple more steps that I could rush, but that's not the idea. Is not to rush, but for you to understand. In fact, maybe this is a good thing for you guys to play with. Here's homework, not to be handed in, but just for your understanding. Homework. Not to be handed in. Play. I gave you the starting point. Of course, you can Google and say, well, you can look up the solution to the Pythagorean. How do you prove this Fermat's last theorem for the exponent 4? Don't do that. Play with this. Play with these equations and what you know. Let me not give it away. And what you know about Pythagorean triples to see if you can find and finish the proof. Let me not give it away. I got you started. This is the first key step. You found a new Pythagorean triple. So the point is, the hint is that s squared plus x squared is equal to r squared. This is a new primitive Pythagorean triple. You have to argue that it's primitive. It's not hard. So it has a parametrization. And follow that down. So this has a parametrization. Dot, dot, dot. What goes wrong? If you can start doing this, what goes wrong? That's the key. Okay? Any questions?